Hello, this is Dr. Liu. In this video, I have two example problems of static equilibrium. So static equilibrium means things are not moving, they're also not accelerating. So let's go ahead and do a problem like these. It's easier because there's no acceleration. Okay, so the first problem comes from University Physics, published by OpenStax, Chapter 6, problem number 26. Find the tension in each of the three cables supporting the traffic light if it weighs this much newtons. So 2 times 10 to the second, so 200 newtons of weight. We'll talk about that. Let's take a look at the diagram. So we have the traffic light, and the cables are basically supporting it. So there's one cable with a tension this way, another cable with tension this way, a third cable with tension pulling down. So we can just focus over here and imagine this point here being pulled by three separate tensions, and yet it doesn't move or accelerate. So this point is at equilibrium, and that could involve all the three tensions, so we can solve the tensions out. Okay, so one of the other tension forces is going to be along here. I'll draw an arrow because they already have the tension here. I'll draw another arrow here, and let's draw it here. So I'm making sure that I'm not letting the exact length of the cable somehow dictate my impression of how much the force has to be. Imagine that there's maybe a little bit of lower hanging here, and this cable is shorter. Will the cable's force change? I don't think it should change, just because the cable is slightly shorter, right? What if you have to hold on to this portion because that anchor is blown? Well, you still have to pull at the same force that anchor was pulling, right? So the length of cable, let's not be misled by that. All right, and now there's also third tension force downward. And what's missing would be the axes. So let's draw out the x and y axes. So this is an x-axis, and this is the y-axis. Okay, so that's the y-axis, and let's move the angles down to the origin. So we have a horizontal line, slanted line, 63 degrees. Horizontal line, slanted line. So this must be 63 degrees, 63.0. And same thing applies here, parallel lines, right? Both horizontal. So this angle is 41 degrees. Okay, and these two forces both have to be decomposed into their components so that we can count them in the x and y axis. So let's see if I can move that angle. Okay, I'll move the angle away. Okay, I'll move the angles away so I can do some decomposition. And this is, as that says T1, so T1x points toward the left, and the horizontal line, this is T1y, so T1y. And draw up this line here. This amount is T2x, a vector, and its vertical component over here is T2y. So let's draw here T2y is this. All right, so a bit crammed in there. Sorry about that. Okay, so now we have the forces in the x and y directions. We can use our Newton's laws. So first, let's say that T1 x is T1 times cosine, and this angle 41 degrees. I want to keep it as positive so I can put explicit negative signs in front of it. So this is something something times T1, so let's keep a blank space so we can later pop up the calculator and do everything in a batch. And T1y is T1 sine 41 degrees. So that turns into a number times T1. And with T2, T2x is T2 cosine 63 degrees. So that's this times T2. And then T2y is T2 sine 63 degrees. Something times T2. Alright, so let's get the calculator out. We'll start calculating. So first we want to do cosine and sine 41 degrees. So, okay, cosine 41 degrees. Oops. Sine 41 degrees. Then the 63 degrees. Cosine 63 degrees. Sine 63 degrees. Okay, so there's a lot of numbers. We'll copy two at a time. So for the 41 degree angle, cosine is 755, sine 656. So 0.755, 656. Okay, so for the 63 degree angle, cosine is 0.454 and sine is 891. 454891. 0.454, oops. 0.891. Okay, let's check. 891, 454, 656, and 755. Okay, so we have all the components, although we don't have the tensions yet. And we also have the W, or the weight, which is equal to T3. That's 200 newtons. Because we know weight is equal to mass times gravity, so we can, if we want, find mass. Mass is 200 newtons divided by 9.8. So this is approximately equal to 200 over 10, 20. So 20.4 kilograms if we wish to find the mass. Now we have the mass. Okay, so let's use Newton's laws. In the x direction, the net forces will add to 0. So the x direction, let's see. There's a T2x, T1x. T2x is positive. Along the x direction, T1x is negative. So, okay, T2x minus T1x equals 0. The 0 was supposed to be mass times acceleration, but we have equilibrium, right? So there's no acceleration. That's why that was a 0. Okay, so T2x is this 0.454 T2 minus T1x is this 0.755 T1 equals 0. You can't really solve it because there are two unknowns. So now let's go ahead and do the other Newton's second law equation. Net force in y adds to 0 because there's equilibrium in y as well, so there's no acceleration in y, and this side is mass 0 acceleration, so it's 0. So now we have T2y, T1y, they're both pointing up, and there's T3 pointing down. So T1y plus T2y minus T3 equals 0. And T1y is this. So 0.656 T1. T2y is 0.891 T2. And then minus T3, which was known to be equal to the weight, so 200 equals 0. So now we have a system of two equations and two unknowns, t1 and t2. The way to solve them is still, and what I propose is to do substitution. So let's do some substitution. Let's call these equations by numbers. So let's call that equation 1, that equation 2, and now there are system equations. I use a curly brace, and then from equation 1 I can say that 0.454 T2 is equal to 0.755 T1, so that T2 is equal to, so 755 over 454. 755 over 454. No need to type in the decimals right there. Okay, so 1.66. 1.66 T1. Okay, so now I can use this to substitute into equation 2. So equation 1 into equation 2. Now I have 0.656 T1 plus 0.891. T2 is replaced by T1, 1.66 T1 minus 200 equals 0. So I can combine these two terms of T1. So let's combine them. 0.656 plus 0.891 times 1.66. So that's how many T1s. Okay, so we have 2.135, 2.14 T1. So 2.14 T1 is equal to 200. So then T1 is equal to, so 200 divided by 2.14. So T1 is 93.4 if I round to even, 93.4. So 93.4 newtons. And then I can take this and just plug it back into that substitution to get T2. So now T2 is equal to 1.66 times T1, 93.4. Calculator. So 1.66 times 93.4. So I have 155. So T2 is 155 newtons. Okay. So basically this one is a little less than 100 newtons. This one's 150, a little over 550 newtons. And if you looked at the lines, this cable is actually longer than that cable, but this force is actually less than this force. But don't make a conclusion about the length and the forces, because that is arbitrary. Just like I said, if I had this little kind of overhang right here to shorten the cable, or maybe I have like an angled pole, that could happen, right? Some of the intersections have these kind of arch over thing, right? So the length is not really a good indicator at all about the amount of forces. So don't try to find the length. Well, you can, right? You have only two angles. You don't have a length to find these lengths, and they're useless. So what are useful are these angles. These angles determine how much forces a component of one force need to balance the other component of force, and that can tell you about the magnitude. Okay, so that was one question. So now with this one done, let's look at the second question, also from University of Physics, published by OpenStax, Chapter 6, Question 30. After a mishap, a 76 kilogram circus performer clings to a trapeze. Oh, well, okay, that's bad. Which is being pulled to the side by another circus artist, as shown here. Okay, so must be difficult to do that. So calculate the tension in the two ropes if the person is momentarily motionless. That means this guy is just hanging on to the rope, and he doesn't want to pull hard because that could accelerate her and maybe she'll lose her grips. So he just wants to hang on for a moment and think about how to manipulate the rope to get her to safety. So she is at the moment stationary. So she's just like this traffic lamp. All right. So what are we given? We're given a mass. Okay, so just like over here for the traffic light, we didn't get the mass, we got the whole weight. So now we have the mass. We have to calculate for weight, which is mass times gravity. It's not that hard. And the angles have changed. And this angle 10 degrees is with the horizontal, just like the 63 degrees with the horizontal. But this 15 degrees is not really with horizontal, it's with vertical. So this angle that we were actually using is going to be the complementary angle to the 15 degrees, right? So it's 75 degrees. All right. And we need to draw a free body diagram for this. So let's start by adding the axes. So this is the x-axis. And this one just gonna serve her hands. That's y-axis. Okay, so the forces have already been marked. This force that is not in the x or y direction, so we decompose this into T2x. And here's also a teeny bit of T2, let's make it bigger, T2y. Upward, mostly horizontal to the right. And the T1 is just the opposite, it's mostly upward. So this is T1y, but very little bit in the x. So T1x. Alright. And this angle, because 15 degrees is with the vertical, and this is the complementary angle. So this angle is 75 degrees. 90 minus 15, right? So that's right here, 75 degrees. Okay, so we can replicate what we did with the the traffic light, right? So we first do some decompositions. We use different. Actually, we use different angles, but the T1 is still the left side and T2 is still the right side. So let's just copy this whole thing down. Can I do that? Okay, so we got this whole thing. Doesn't exactly fit, so let's do this. Let's move okay. Horizontal stroke wasn't included. Let's kind of stack them together. Okay. A bit messy. Okay. So we'll get rid of the angles, get rid of this quantity, get rid of that, get rid of this quantity. Right, so our goal is to see the patterns emerge from behind the numbers. Let's just move that over to the right, since we weren't really being squeezed by that end of the line anymore. So alright, the angle in the T1 is 75 degrees, so 75 degrees. 75 degrees. The other angle is 10 degrees. 10 and 10. Okay, so let's call up the calculator to do 75 and the 10. Okay, I got all the values. So the 75-degree pair values 259 and the 966. Okay. 259, 966. And the 10-degree angle pair values 985 and 174. Okay. So now we have the components, and what else do we need? We need a weight, right? So let's calculate on the right side. The weight is mass times gravity, and this time we're given the mass is 76 kilograms times 9.8. This should give us close to 760. So let's use a calculator. 76 times 9.8, 745. So downward force is 745 newtons. That's equal to the tension. Well, not tension, just the weight. Okay, so we'll do the same exact argument that she was in equilibrium. So net force on her in x direction is 0. So what forces are in x? T2x in the positive x, T1x in the negative x. So T2x minus T1x equals 0. And T2x is this, right? So it's 0.985 T2 minus T1x is this, 0.259 T1 equals 0. Again, we can't really solve it. So we move on to the y direction. Net forces add to 0, no acceleration in y. And y direction, there are two forces up and one down. So T1 y plus T2y minus the weight is equal to 0. So T1y is this, 0.966 T1 plus the T2y right here, 0.174 T2, and gravity was calculated 745 newtons equals 0. So these two equations are again a system of two equations and two unknowns, right? So we can still take equation 1 and turn it into a format that looks like this. So 0.985 T2 equals 0.259 T1. So T2 is equal to the 259 over 985. So 259 over 985, and we have 0.263. So 0.263 T1. Okay, so that's still called equation 1. We can take that and plug it into equation 2 to remove or eliminate T2. So 1 plug into 2, we have 0.966 T1 plus 0.174. T2 is substituted with 0.263 T1. Minus 745, so that's equal to 745. And then we can combine these two factors and divide 745 by this factor. So T1, let's combine the factors first. So 0.966 plus 0.174 times 0.263. So that's 1.01 of T1. And let's just do it all together. 745 over the 1.01. So 738. So here's 1.01 T1 equals 745. So T1 is 730, is that 738? 738 newtons. So now we can take it and put it back into this equation we use for substitution. Alright, so now basically equation 2 back to equation 1, if you like. This is that equation 2. So equation 1 becomes T2 equals 0.263 times T1, which is 738. Let's use our calculator. So 738 times 0.263. So we have force 194 newtons. So 194 newtons. Alright, so that solves both problems. We'll basically run through exactly the same type of problem two times, so you get to see how it's solved 2 times. And make sure you draw your free body diagram, make sure you find the correct angles, bring the angles down to the origin. And that's what I did. I realized, oh, the 15 degrees here is not with the origin here. This one with the axis is 75 degrees. And then I use that knowledge to decompose the forces, and then use Newton's laws to write 2 equations, one from each axis, each dimension. And then you'll end up with 2 equations. If you have 2 unknowns appearing in both equations, use substitution to solve that system of equations so you can get both forces. Thank you.